So welcome everybody to the GOTO conference in Copenhagen. My name is Stefan Edlich. I wrote the first two NoSQL books and I run a lot of NoSQL conferences. And I'm very happy to have Ian Plosker here at the GOTO conference. Welcome, Ian.
Well, thank you for having me.
Yeah, just to start, tell us a little about yourself.
So I work for Basho Technologies, the makers of React. I am the technical lead of international operations based out of London, and just here in Europe talking about React, getting people interested.
So tell us please, how did you get into the database space?
So previous to working at Basho, I was working for a company building basically what amounted to CMSs, and also worked on a large-scale bioinformatics project, and traditional relational databases didn't really fit the problem, so I started exploring alternative databases, stumbled upon React, and the rest is history.
Mm-hmm. Okay, so we will talk a little about React, of course, because it's an interesting database. Can you tell us, when I first met React, I learned that it is a key-value database, but it can understand JSON and parse JSON. So what it is, a key-value or a document database?
So it's a key-value database, but you can use it as a document database because React is agnostic to what your values are. To React, it's a binary blob, which isn't 100% true because we have a feature called React Search, which allows you to do full-text indexes based on your values, assuming they're either plain text, XML, or JSON. So it sort of blurs the line between key value and document store.
One question comes to my mind. Do you also have some use cases which are a little close to the graph space because you have link walking, I think?
Yeah, so I mean, you can build lightweight graphs using links, potentially social graphs, but React isn't a graph database. Our links are essentially one-way relationships between objects, almost like hyperlinks in a web page. So maybe if you had a small social network where people had a limited number of friends, you could use links to express those relationships. But you can do the same with our secondary indexing feature as well.
Okay, I learned from the website that there are several versions of React, like CS, Core, Enterprise. Can you tell us what the differences are?
So it's a little bit complicated. In terms of products, there's really three products that Basho makes. The first one is React. React is the open source database. It's the open source distributed database that all of our other products are built on top of. React Enterprise or React EDS is the commercial version of React, and we add a few other features, including multi-data center replication as well as support. React CS is a new product we launched about 2 months ago, and React CS, React Cloud Store, is basically a version of React that allows you to build your own cloud storage service. You can build your own S3. It actually has an S3 compatible API, and you can store large objects in it. But it's actually built on top of React. So.
Okay. In the discussions with Andy Gross, I learned that React is operational strong. Can you tell us why?
So the reason why React is operationally strong, first off, is it's a distributed database. So losing one node doesn't take your application down. So it's tolerant to failures. Your operational staff may not even need to wake up in the middle of the night if a server crashes. They can deal with it in the morning. On top of that, when you need to scale out, when you've run out of storage capacity, throughput, processing, you can simply add a node by bringing a new server, a new VM online, installing React on it, and telling it to join the cluster. And it's just that easy. I think few other databases out there have a horizontal scaling story that's as simple as React's. On top of that, React is very easy to work with, especially from the operational perspective. Cluster membership, managing your cluster, as well as tolerating the real world failures that you experience in distributed systems is all sort of thought through in the product. So we really pride ourselves on our fault tolerance. And that's, I think, the key to operational ease. Failures are, I think the whole point of a distributed database is that it should be able to transparently survive failure.
There's several, I think, monitoring solutions you advertise, like React Control and React Agnostic. Can you tell us a little bit about these?
So I'll start with React Agnostic. The idea of React Agnostic is simply that we've identified the most common support problems we have, and we've built a tool that just tells users they can run it against a React node, and will say, here's a configuration issue you might have. You should probably fix it. For example, if you had mounted a disk without turning on no A time, meaning that you don't mark access time every time a file is accessed, which adds simply latency to your database. Or, for example, React will use a large number of file handles, and most operating systems limit the number of file handles a process can have open to 1024. So React can use quite a bit more than that. So we'll warn you if, for example, your file handle limit is too low. So React Control is actually a cluster monitoring tool that allows you to actually add and remove nodes from a cluster, get some idea of what parts of the ring they own, and give you some visibility into what React's doing from a simple web interface.
Do you have some feedbacks from your live customers, or what can go wrong?
So, yeah, there's a lot of interesting cases. Actually, one of the most common issues are simply running distributed systems is really hard, and we may even provide software that helps people run distributed systems, but the hardware around distributed systems are really hard, and so we've repeatedly run into the same problems with customers. One common one is called TCP incast, where buffers on switches are overrun when one node sends out messages to a number of nodes, which all send back messages at the same time to that original sending node.
These internal messages? React internal?
Yeah,
or
React
external to the
internal.
customer?
No, React internal messages. So one node may go out to 3 other nodes and say, give me all of the replicas of this piece of associated with this key, and send them all back. Or, for example, we have things that are called coverage queries. If I wanted to see, do a range query with our secondary index feature, it would go out to actually a covering set of the key space, which means that you go to a normally configured cluster, 1/3 of all nodes, and all of those messages are routed back, and it's very quick to overrun the, especially in cheap switches, the switch buffers, and you get this degenerate case where your TCP or where your Ethernet performance isn't being fully utilized, where you might only be using 10% of it because you have this weird behavior from both the Linux kernel's TCP stack as well as your switches. So yeah, that's a problem we've run into a number of times. It's interesting. Most of the time when I actually see failures with React, once we've gotten past some of the initial common pitfalls, if React starts failing, it's usually a sign of hardware problems, that the disk is about to fail. But there are common problems. In fact, that's the point of React Agnostic, is to find those common issues that we've seen over and over again and warn people before they have to call us and ask us what's going on.
But I assume this is the valuable internal knowledge you capture internally, and you're not publishing this knowledge already, or these fail. What can happen and how you react in these cases?
So I mean, common sorts of failures are hardware failure. A disk goes out, and React should transparently survive that, assuming that you have enough nodes, assuming that you have 4 or more nodes. And in those cases, I mean, you basically, if the machine is not recoverable, then you fix it and you remove the node from the cluster saying this machine is dead, it's no longer part of the cluster, I'm never going to be able to bring it back. Once you repair that server or bring a new server in, you tell it to join, and the cluster returns to health. So actually, maybe you want to talk about anti-entropy now, because I think that actually fits in here.
Yeah, this is also one question. So
yeah. So
what is anti-entropy?
What is anti-entropy? Yeah, anti-entropy. So entropy is the concept of things becoming more disorganized over time in physics, right? Things becoming more random and less organized. So REOC is an eventually consistent system. It doesn't enforce strong consistency. So what that means, at any given time, different nodes in the cluster can have a different idea about what a certain key, what its value is. And one of them is more correct than the other. One of them is the value you actually want. So for example, if you had a node go down during a write, and the write only goes to 2 nodes, and one of the nodes missed it, then that node that was down or partitioned
has different knowledge.
Yeah, has different knowledge, and when you come back and request that data in a read, REOC will ask all of those nodes for the data. And when it finds that one of them has a different piece of data, an older version, it will do something called read repair, which will update it with the newest version. That's a form of anti-entropy. The idea of anti-entropy is that it's bringing things back to an orderly state.
Minimize diversity.
Yes, exactly. So it's moving things back towards consistency. So there's a few mechanisms in REOC for anti-entropy. There's another called hinted handoff. So for example, a node gets partitioned or goes down and a write comes in. Actually what will happen is another node will take over for it, will spin up a fallback partition. And that fallback partition will accept the write in lieu of that other node. And when that other node comes back online, the fallback partition will be transferred, will be handed off to the primary owner of it, and it will get all of the data, all of the writes that it had missed in that time. So that's sort of a form of anti-entropy as well. Those are the two forms of anti-entropy in open source REOC. The Enterprise Edition has another form because it actually does multi-data center replication. So you actually put clusters in multiple data centers and you can synchronize them. So that synchronization is a form of anti-entropy as well. So so the point of having these tools for bringing the system back into an orderly state is part of being able to survive failures. It's not just surviving them, but also being able to recover from them and getting back to an orderly state. Because in a normally operating REOC cluster, you really shouldn't have much entropy at all. You shouldn't have the system becoming disorderly. This is really only for fixing issues after some failure happened. But very often we don't even notice failures that happen in running systems. A machine can become partitioned temporarily, or an operating system can do something crazy for a little bit and get back to reality after a moment and start accepting writes and reads normally. So it's so anti-entropy is only necessary following some sort of failure.
Okay. One question I have is concerning third-party tools. Sometimes I see out there in the open source scene or in software as a service, there are some companies who offer third-party solutions for monitor and diagnostics. Is there also something for REOC already?
So third-party tools for monitoring and diagnostics. I'm not familiar with any commercial tools for monitoring REOC, although there's a number of tools out there that do integrate with REOC for monitoring. One of them is actually developed by a community member. The tool is called Riemann. It's actually designed just for monitoring servers, but also monitoring different pieces of software, MySQL, React, etc., and collecting stats from them and displaying it in through the web. So there are tools out there. I mean, there are vendors who will integrate our stats. React exposes all of its statistics that it collects over an HTTP endpoint. For example, you can find out what the average response times for GET and WRITE requests are, what the 95th percentile GET and WRITE response times are, know how many writes were done in the past 60 seconds or since the React node was brought online. And all of those are exposed over an HTTP endpoint, so you can pull those into any tool and parse them. The Enterprise Edition also exposes the same stats over SNMP or JMX if you already have infrastructure that knows how to use those stats. So there's a lot of monitoring tools that are off the shelf that are designed for React that will integrate with it.
But you can use the statistics.
So you can use the statistics and pull them into whatever tool you might use. And there's a number of vendors with really great monitoring tools out there that can take advantage of React's statistics.
Okay, my next question is concerning a little the competition, and specifically DynamoDB. The launch of DynamoDB this January was a huge bomb, I think. So, what do you think of this database, and what is the position, the specific use cases? How do you value these two solutions?
So DynamoDB is really interesting. I'm blown away by Amazon's ability to put out new products on a regular basis. It's unbelievable to see such a large company be so productive and release new things. But DynamoDB is interesting. It provides a database as a service. It's really appealing if you're already running your applications on Amazon, if you're running on EC2, if you have data in SimpleDB but need something a little bit more powerful. I think the biggest limitations of it that you're running on Amazon's hardware. So for companies that or people who want control of their infrastructure, want control of their data for security reasons, or just for peace of mind, will run elsewhere. I also think Amazon's pricing is really high because you pay for the number of requests per second you want to be able to do. And their pricing, in fact, there's someone in our community, and I'm at a loss for his name right now, who's actually written a bit about why Amazon's pricing doesn't actually fit their cost for doing it, and you are paying a pretty large premium for using DynamoDB. It would actually be cheaper to run React at some point very quickly.
Could also be that the writes are expensive because they're writing on SSDs.
It could be. I think so part of it is they charge more for eventually consistent write versus a consistent write. And the way they've priced it, it probably costs them marginally more to do a consistent write than an eventually consistent write. So the pricing is simple, but it may not be the best, and paying for actually usage may not be best for a lot of applications, especially ones that are high load. It's an interesting product. The other limitation of DynamoDB, and I don't remember the exact size, but they have a hard limit on the size of values. I think it's in the, may even be in the kilobytes, but I don't remember.
64 kilobytes or something like that.
Whereas React practically, it doesn't have any hard limit. Practically, you probably wouldn't want to write something much larger than 10 megabytes for best performance, nothing larger than a megabyte, but we don't impose any hard restrictions. So for a lot of applications, 64 kilobytes is not very much.
And I think there are also some differences in terms of the data model, because DynamoDB has some key value, and you have full JSON. And is this something?
Yeah, it's a different data model. React also offers some different ways of querying your data. And they're different products, and I think they solve different problems, and I think that's actually common throughout the NoSQL space, that everyone gets lumped into this one category, but the category is really a category of categories, and everyone does something different, and these databases aren't interchangeable. All of them have particular things they're good at. I mean, there's some overlap, but none of them solve every problem, and it's the same with DynamoDB. So I think React and DynamoDB could even be complementary in an organization. Could solve different problems. So.
Okay, my next question is concerning, you favor the consistent hashing model, whereas other databases or competitors do sharding. What do you think are the use cases or advances of each of these?
So the great thing about consistent hashing, for example, is it allows us to scale really easily. Part of the reason why horizontal scaling is so easy is because we use consistent hashing. We don't need to split shards when we scale. We don't need to resize shards, and that can be pretty painful. Also, hotspotting is a problem with shards because the data isn't organized based on it's based on some shard key, and the shard key doesn't really take into account where the most commonly accessed data will be. With consistent hashing, the data is kind of relatively randomly spread out through your cluster, so you're much less likely to get hot spotting. Now, the nice thing about sharding is efficient range queries. That's really what you lose. So for me, my favorite use case where sharding is interesting is something like a sharded Solr, like Elasticsearch, full text search, where efficient range queries are really appealing. That said, you don't always need range queries when you're doing full text search. If you're doing mainly single term queries, then you're not doing range, and sharding doesn't make a difference there. In fact, you actually get some advantages from doing consistent hashing because the load's more evenly distributed around the cluster.
So you would say that there are some use cases, let's say 5, 10 or 20%, where sharding might be useful. Say if I want to have a specific bunch of data on a specific server, then it's easier to control. But
So I think there's a difference between when you might want to group data, have data co-locality. There's databases that don't use sharding, but do allow you to co-locate data. So, something like Cassandra with column families, you can sort of associate data in the column family and get some co-locality. And, but it isn't quite sharding. It's, it is using consistent hashing still. For me, the sharding is useful, really when you want those to maximize the performance of range queries. So
that's good. One interesting feature I always liked in React is having the pluggable persistence. And I was very happy to read that you also support LevelDB.
Yep.
What are your experiences with LevelDB?
So there's a few reasons why we added LevelDB. Our default storage backend is called Bitcask. Bitcask is great. Bitcask is the default for good reason. It has a really flat latency profile. The reason why is we can guarantee that for any read or write you do at most one seek. That's because Bitcask is just a log with an in-memory key lookup table that has a pointer to where in the log that the associated value is. So any lookup is simply a lookup in the hash table and then a seek on disk. And a write is just maybe you're already at the end of the end of the log file, but worst case is you have to seek to the end of the log file and append to it. So really flat latency profile. The problem with it is all keys must fit in memory. Not all your values, all your keys, and remember it's a cluster, you can always get more memory by adding more nodes. But LevelDB allows you to have sort of data sets of unbounded size. It doesn't store all keys in memory. So on top of that, we've added a feature to React called secondary indexes, which are only supported by LevelDB. The reason why that is LevelDB is actually ordered on disk. So we can do efficient range queries at the storage backend. So I'm pretty excited. The next version of React, which should be shipping in a few months, we'll include a new version of LevelDB that includes bloom filters. And those bloom filters will actually really improve the performance of LevelDB, especially in the cases where you might have a key that either doesn't exist or you're writing new data. So the latency profile of LevelDB is about to get a lot better.
So what are the bloom filters in specifically?
So step back a bit. LevelDB, I should say, in its worst case, LevelDB might need to do 3 or 4 seeks to determine that either a key exists or doesn't exist and return the value. So what bloom filters allow you to do is in constant time determine whether or not a key is stored in a collection. It basically allows you to determine whether something's a member of a collection in a memory efficient and time efficient way. So the bloom filters save you from having to do a bunch of seeks when a piece of data doesn't exist.
Okay, I don't know in which version you inserted commit hooks.
Yeah.
What are they useful for? Can you give some examples? And what languages can you write code to be executed?
So there's two types of hooks. There's pre and post commit hooks. Pre-commit hooks fire before the data is actually sent out to be persisted on disk. So with a pre-commit hook, internally, React Search does its indexing in a pre-commit hook, so it'll actually extract the full text data and send it out to the indexes to be stored in a pre-commit hook. You could also use it to enforce business rules, to say, given these conditions, don't accept the write, or given these conditions, don't store this data, or append this data, transform the data before you store it. So, and then there's post-commit hooks, which get fired after the data is stored. So actually, post-commit hooks can be used to integrate with other tools. Maybe once you've done a write, you want to send a message to a queuing system saying that, oh, I've successfully written this piece of data. And so you could fire that off in a post-commit hook to, some AMQP implementation. Or,
are you forced to do this in Erlang or?
You can write JavaScript as well. So Erlang or JavaScript. Erlang performs a bit better. I tend to tell people, if you don't know Erlang, maybe you want to prototype your commit hook in JavaScript. JavaScript's more limited. Obviously, integrating with something like a queuing system is not going to be possible because you can't open, a TCP connection from JavaScript. You're pretty much limited to what's possible within a JavaScript VM, whereas in Erlang, you can do anything the Erlang VM supports. So basically anything. You can open TCP connections, you could integrate with, speak to other Erlang nodes, anything that Erlang VM supports. So if it's a simple hook, you can mock it in JavaScript and then, translate it to Erlang.
Okay, one final quick question is,
Sure.
What is the long roadmap, meaning React in 3 years?
What's React in 3 years? That's a good question. I don't know that I'm the right person to ask that, but I think, it's all about continuing to innovate and providing new ways to work with React. React is sits on the favoring availability over consistency in failure scenarios. I think we'd like to explore doing something that favors consistency, or at least allow users to pick stronger consistency than we already offer. We allow people to turn up the consistency knob pretty high, but we don't let them turn it to 11. I think we'd like to do that. I think we'd like to add different mechanisms for anti-entropy that are a little bit more active. Right now, our anti-entropy systems are more user-driven rather than driven by React. So that will be something that we're exploring. And just improving what we have already, building on queryability. I think we have a ways to go in terms of providing different sorts of querying mechanisms or improving the querying mechanisms we already have beyond the primary key lookup, so making React search much more powerful, making secondary indexes more powerful,
Mm.
just allowing users to get at their data in interesting new ways. So it's really building a more robust, more flexible, and easier to query database. I think that's where we're going to continue to move.
Mm-hmm. Okay, thanks a lot for your time. I think
Yeah.
it was very enlightening, and I hope we see you next year.
Thank you.
Thank you.